Hey there, it's Shannon Mapchick-Myers. Today we'll be taking a look at sections 5.6 through 5.8 of the EP text for discrete mathematics with applications. And we're just going to be taking pieces of what we need from these sections in order to prepare us for partial order relations. So, you ready? Let's go. Defining sequences recursively. So a recurrence relation for a sequence, A0, A1, A2, and on, is a formula that relates each term, A sub k, to certain of its predecessors, A sub k minus 1, A sub k minus 2, etc., until we get down to A sub k minus I, where I is an integer with k minus I greater than or equal to 0. So the initial conditions for such a recurrence relation specify the values of A0, A1, ... all the way down to, say, A sub I minus 1 if I is a fixed integer, or A0, A1, A2, ... all the way down to some A sub m, where m is an integer with m greater than or equal to 0 if I depends on this k. So here we go. Looking at an example, what we want to do is find the first 4 terms of a recursively defined sequence given by this formula. So anyway, you guys should be getting pretty used to the notation. The upside down A means for any. The integers are denoted by this z here. This one means such that, okay? So basically, putting it all together, we're defining this sequence v sub k equal to v sub k minus 1 plus v sub k minus 2 plus 1 for any k belonging to the integer such that k is greater than or equal to 3. So we've also been given the initial conditions that, actually, sorry, this is a typo. It should be that V0, or V1 rather, V1 is equal to 1 and V2 is equal to 3. Good so far? All right, so what we want to do is we need to find the first 4 terms of the recursively defined sequence. So here we go. We know V1 and V2, right? So that's easy. We've got the first 2 terms. So let's put that in. V1 is 1 and V2 is 3. Now let's work on V3 and V4. So V3 is going to be equal to, well, 3 is now our k, so that's like the input here. So basically, wherever there's a k, we're going to be putting in 3. Good so far? All right, so this would be V3 minus 1 plus V3 minus 2 plus 1. And so just wherever there was a k, we put in a 3. Well, this is going to give us V2 plus V1 plus 1, but we know that V2 is equal to 3 and V1 is equal to, beautiful, 1. So at the end of the day, V3 is equal to 5. Okay, so we got these other ones because our V2 had an output of 3 and our V1 had an output of 1. Cool, cool? All right, well, how about V4? Again, we'll plug it in wherever we see a K, so that'd be V sub 4 minus 1 plus V sub 4 minus 2 plus 1. And that in turn will give us V3 plus V2 plus 1. So our V4 would be, beautiful, 5 plus 3 plus 1. So we would get V4 is equal to 9. Cool, cool? All right, so just to kind of match up what we did here, wherever there was a K, we plugged in a 4, all right? And then remember that V2 was 3. That's where we got that information. And then our result for V3 had been 5. So in for V3, we put 5, and we got a result of 9. So if you want, you can list them. The first 4 terms are 1, 3, 5, and 9. Cool, cool? All right, very good. So next up, we have this problem, and I have to say I struggled a lot to figure out how to explain this problem to you. As you know, usually I like writing most of the problem out. But anyway, this is how I came up with showing you this problem. Okay, so here we go. In this example, it's a take on something called the Fibonacci sequence. So we've got a single pair of rabbits, male and female, and this pair is born at the beginning of a year. So assume the following conditions. Rabbit pairs are not fertile during their first 2 months of life, but thereafter give birth to 3 new male-female pairs at the end of every month. No rabbits die. So we're going to let S sub n equal the number of pairs of rabbits alive at the end of month n for each integer n greater than or equal to 1, and we're going to let S0 equal 1. So we need to find a recurrence relation, and then from that we're going to find some other info too. So this right here, I know it's not super proper because n starts greater than or equal to 1, but say, hey, they're born. So this is like our S sub 0 is equal to 1. So the rabbits are born, they're not going to be fertile for 2 months, right, after they're born. So here is just sort of a chart, right? We've got our rabbits are born, so they're alive, if you will, at the in between the, you know, times 0 and just before they turn 1 month old, right? So the kind of trick here is that we're going to take a look at and try to find this pattern. So we're going to define this recursively. And so we want to, this column right here, the K, is to check out when this recursive pattern begins, right? What value of K. So this we said was our S sub 0, meaning our first pair is born. I've counted these in pairs. So, all right, basically they're alive at the end of month 0, beginning of month 1, right? And then they are, but they're not ready to breed, right? And then they become ready to breed at what? This juncture here, right? Because 2 months before they were born. Cool so far? So what happens is we take a look at this here, and then we want to figure out when our trend begins, all right? So what we have is at the end of month 1, right, which is here, 1 pair of rabbits is alive, and 0 pairs of rabbits are ready, have been fertile during that month 1. At the end of month 2, right, we're gonna have another, the rabbits are alive and they're fertile now, okay? Or you could think of it as they were alive 2 months ago, so now they're fertile. Cool, cool? So then becomes a trend of giving birth, right? So the ones highlighted in yellow represent this very first pair of rabbits, okay? And so then what happens is once they become fertile, right here, then at the end of month 3, all right, so now I'm over here at the end of month 3, they give birth to 3 pairs of rabbits. So there's 4 pairs of rabbits which are alive. Cool so far? All right. But during month 3, the only rabbits that are fertile are that original pair. Cool so far? So if you look at this trend, right, you're going to have this gap of 2 months after each pair is born, then they become fertile during that month. So here, do you see that this represents right here where the 3 pairs of rabbits that were born from the first pair of rabbits is ready to breed, okay? And that corresponds to this highlighted 3 right here. So then what happens is you take a look, and each time the original pair breeds 3 pairs of rabbits. And then after 2 months after birth, each pair becomes fertile. So you kind of keep going and going and going. And let's see if we can kind of look at any patterns, right? Because we obviously don't want to keep writing all this stuff out forever, right? So let's take a look. I mean, do you see that we definitely have some things that are matching up? Do you see we've got 4 and 4 right here, and then 7 and 7. And how many months apart are these things? Do you see the 10 and the 10, the 22 and the 22? So basically, what do you think is going to happen? Beautiful. We're going to start our K at 3. It's got to be greater than or equal to 3, because that's when our repeating trend is going to start occurring. So let's take a look at what happened. You're going to be adding each successive month, you're going to be adding rabbits to the amount that you had before. So if we take a look at month 9, right, we're definitely going to have as many rabbits as we had during month 8, at the end of month 8. So that's got to be our starting point. Do you agree? But then what's going to happen here is that 22 rabbits are going to be ready to breed, right? Now, if we want to take a look at this, we don't want to have 2 separate columns, right? So do you see that 2 steps back is where if you think about 2 terms back, thinking of sequences, that's where we have that number 22. And how many babies are they going to have? Well, they're going to have, each of these 22 pairs is going to have 3 babies, right? So at the end of month 9, you'll have what? How many babies? Good. 73 plus 3 times 22, because that's the number of new babies. And so that is going to be 139. Awesome. What about month 10? Good. You're going to have 139 plus 3 times. Good. You got to go the term before for the 139, right? And then you got to go 2 back to the 43, but then you got to times that 43 by 3, right? So for that, we'll get what? 129 plus 139. So on that 10th month, we will have, I think it's 268 pairs of rabbits. Cool, cool. All right, and then going further, we have at the end of month 11, beautiful, 268 plus 3 times. Awesome. 73, which is 487. Beautiful. And then at the end of 12 months, at the end of the year, you'll have how many? 487 rabbits plus 3 times 139. Good. 904 pairs of rabbits, right? So in general, right, our sequence for this would be S sub k is going to be the amount of rabbits from the month before, right? Which we could denote as S sub k minus 1 plus 3 times 2 terms before, right? And so then we have our general formula there. So that's our general formula. So at the end of the year, from 1 pair of rabbits, 904 pairs of rabbits will be alive. Amazing, isn't it? All right. So now let's take a look at solving recurrences by iteration. So the most basic method for finding an explicit formula for a recursively defined sequence is iteration. Iteration requires that you start from the initial conditions and calculate successive terms until you see a pattern emerging. At that point, you guess an explicit formula and then you see if it checks out. So in this example, we're going to use iteration to guess an explicit formula for this recursively defined sequence. And then we're going to use mathematical induction to see if we're correct. All right. So here we go. This one, do you see how we're going to always have, 2 times 3 to some power? Okay. So we may want to bring to mind, there was a formula, I think, for geometric stuff. It was a while ago. So it turns out that the summation from I equals 0 to n of r to the I is equal to r raised to the n plus 1 and then minus 1 divided by r minus 1. So we're just going to kind of put this in our back pocket until we might need it. All right? So let's just start finding some terms and looking at a pattern. And one of the tricks to this is instead of just writing the result, right? Because remember with the rabbit one, we kept writing out the pattern until we, figured out what it was. So here, we're going to do the same kind of thing until we figure it out. So we know that P1 is equal to 2, right? So P2 is going to equal to, good, P2 minus 1, I'll go a little slower at first, plus 2 times 3 to the 1 to the square. And how did I get this? Because wherever we see a K, we're plugging in a 2, right? Because we're on term P sub 2. So that equals what? Well, P1 plus 2 times 3 squared, which equals 2 plus 2 times 3 squared. I don't even really care what that is. I want to find a pattern, so I'm not even going to say what number it equals. Good so far? All right, so P3 is going to be P sub 3 minus 1 plus 2 times 3 cubed. Again, wherever I see a K, I put in a 3. This is going to yield P2 plus 2 times 3 cubed. Well, what was P2? P2 was 2 plus 2 times 3 squared, right? And then we're adding 2 times 3 cubed. Cool so far? All right, well, let's do another one. P4 would be P sub 4 minus 1 plus 2 times 3 to the 4th. For the reasons we mentioned before, that's going to give us, awesome, P3 plus 2 times 3 to the 4th. Well, what was P3? P3 was 2 plus 2 times 3 squared plus 2 times 3 cubed. And then we'll have to add plus 2 times 3 to the 4th. Cool, cool? All right. Well, okay, well, what do you think? I mean, is there enough for us to find some sort of pattern? I think so. Let's check it out. We're going to work with this one a little bit and think to ourselves, all right, well, P4 is equal to all of this here, right? Well, we could certainly write it like this, couldn't we? We could just write it like 2 plus 2 times 3 squared plus 2 times 3 cubed plus 2 times 3 to the 4th, because those parentheses were just grouping what the term before was, right? So this here was just grouping that this was our P3, and this one right here was showing us that this was our P2. Cool, cool. All right, so now what we have going on is we certainly could do what? Well, we could factor out a 2, right? And if we factored out a 2, what would we have? We'd have 1 plus 3 squared, right? Plus 3 cubed plus 3 to the 4th. Well, that would have been really cool if this had been like 1 times 3 to the 1, right? But this 1 doesn't lend itself to the pattern. Well, okay. Wouldn't you agree that we could write this as 2 plus 2 times 3 squared plus 3 cubed plus 3 to the 4th? Good so far? I just kind of played around, rewrote it, decided that first term wouldn't work, so went ahead and pulled it out of there. And okay. All right, well, we're almost there, but you know, it's really cool. Wouldn't it be really cool to be able to, since we have this summation that starts at 0, right? Wouldn't it be cool if our trend started at 0? So how could we do that? We could say 2 plus 2 times 3 squared, right? And then we would have 3 to the 0, wouldn't we? Plus 3 to the 1 plus 3 squared. Cool so far? So we could rewrite this one as what? 2 plus, this is what, 18, times the summation from I equals 0 to 2 of what? Good. 3 to the I, if we wanted. All right, cool. Well, that's all well and good, but wouldn't it be nice to have a formula that would work for n? So p sub n would be what? We still have this 2 plus the 18 won't change, right? And here, everything had been decreased. If you take a look from term by term, do you see that the difference is the power decreased by 2 on the base of 3, right? So in general, we could write this as 2 plus 18 times the summation from I equals 0 to what? Instead of n, we'd be writing n minus 2, wouldn't we? Cool so far? Because we decreased each power by 2. And then this would be 3 to the I, and that is going to represent our summation. Cool. And now we want to fit it in with this stuff over here, right? So if we take a look, we need to add 1 to the top limit of the summation, right? In order to get this formula here. So when we do so, our p sub n would be equal to 2 plus 18 times, well, the r, would you agree, is awesome, 3, right? And then n for the n, if you will. So actually, let me erase that. And then we're going to say just the n, okay? So n for the n, we're going to put in n minus 2, all right? So that will end up being what? 3 raised to the n minus 2, and then we have to add 1. We're going to subtract 1 from that, and that's going to be over 3 minus 1. And so again, this is what we're plugging in for the n in this geometric formula over here. And so simplifying, we will have our nth term would be 2 plus, well, do you see this right here is going to be 2, so we'll get a 9 right here. And then 3 to the n minus 2 is going to be, plus 1 is going to be 3 to the n minus 1. And don't forget about that minus 1 still hanging around. Okay, so now here p sub n would be 2 plus 9 times 3 raised to the n minus 1, and then distributing, we'd have minus 9. But 9 is 3 squared, isn't it? So you'd have 2 plus 3 squared times 3 to the n minus 1, and then 2 minus 9 is minus 7. So at the end of the day, our p sub n will be 3 to the n plus 1 minus 7. Cool? And that would be, you know, for any n which belongs to the set of integers such that n is greater than or equal to 1. So here we've taken this from something that is defined recursively, right, to something that is explicit. So now we need to prove it. Good so far? So that was our plan here. And now we need to prove that it's true. So we'll use mathematical induction, right? And so here we go. Okay, so we're going to show that our new formula is true, okay, by utilizing this formula with its initial condition that we know is true. All right, so here we go. First, we have to define everything. All right, so we're going to let P sub 1, P sub 2, P sub 3, ... be a sequence that satisfies the recurrence relation that we started with. And what was that? It was P sub k was equal to P sub k minus 1 plus 2 times 3 to the k with an initial condition P1 was equal to 2, and we have to define k, and this would be k belonging to the integers such that, and what was k? K was greater than or equal to 2. Good, good? We're going to also let the property P at n be the equation P sub n is equal to 3 to the n plus 1 minus 7. Okay? All right, so now we need our basis step. Our basis step, if you remember, is we need to show that when we plug in that first value of n, we will what? Have something which is true. All right? So here we go. Remember, we're utilizing the fact that we're looking at this one, okay? So we know that's true. But what was P1? I mean, P sub 1 is what? Equal to 2, right? All right, well now let's use our other one. One is equal to 3 raised to the 1 plus 1 minus 7, which is 3 squared minus 7, which is 2. So that checks out. They are equal. Good so far? All right, our inductive step So for our inductive step, what do we need to do? Well, we need to show that the k plus first term in our property is also true. Okay? So here, what will P sub k be? Or P at k? So P at K is going to be, remember we're using this, 3 to the K plus 1 minus 7. Good so far? So, what is P at K plus 1? That's going to be 3 raised to the K plus 1 minus 7. Good so far? Which is equal to 3 to the K plus 2 minus 7. All right, well, what do we know? We know what P sub K is, right? And so let's take a look now at this situation here, okay? So, looking at that one, we've got P sub K plus 1 is going to equal to P sub K plus 1 minus 1 plus 2 times 3 to the K plus 1. Good so far? Okay, well, this is equal to P sub K plus 2 times 3 to the K plus 1. But what was P sub K? P sub K was, beautiful, 3 to the K plus 1 minus 7. And then we'll have plus 2 times 3 to the K plus 1. But notice that we have a common factor of 3 to the K plus 1, don't we? So this is going to give us, so do you notice here I have one of those 3 to the K plus 1s, right? And here I have 2 of them. And they're going to be what? They're going to be like terms, aren't they? So I will have 3 of them. So I have 3 of these 3 to the K plus 1s. And then we've got this minus 7 carrying it over from here. Well, that's going to be, remember, 3 is 3 to the 1. So I'll end up getting 3 to the K plus 2 minus 7. But isn't that what we got over here? And so, therefore, we've shown what we needed to show, and we're all set. We're done with our proof. Our property is verified. Okay, so next up, we've got this definition. A sequence A0, A1, A2, continuing in that manner, is called an arithmetic sequence if and only if there is a constant d such that a sub k equal to a sub k minus 1 plus d for all integers k greater than or equal to 1. So it follows from that that a sub n would equal to a0, okay, and then plus, well, you'll have d added to itself n times, so that's d times n for all integers n greater than or equal to 0. Cool, cool? So let's look at an example. So example 4, we've got a runner. She targets herself to improve her time on a certain course by 3 seconds a day. If on day 0 she runs the course in 3 minutes, how fast must she run on day 14 to stay on target? So, first of all, 3 minutes is equal to what? How many seconds? Because we have two different units of time. Well, there's 60 seconds for each minute, so do you see we'd have 180 seconds? So on day 0, all right, call it A0, she runs the course in 180 seconds. We'll put the units on at the end. Now, every day she wants to decrease it by 3, and so this common difference would be what? -3. All right? So you could think of it as adding this difference. All right, so A1 is going to have to be what? Well, the initial day, right? The initial time. And then plus what? The common difference times what? Well, this is the second time she's running it, and so it would be the common difference just times 1, right? But A2 would be the first time plus that common difference times 2, etc., right? So for us, we would have A sub n would be 180 minus 3 times n, because we're decreasing it by 3 seconds each day. And so on day 14, she would need to run the course in 180 seconds minus 3 times 14 seconds. So that would end up being 138 seconds. So in conclusion, on day 14, the runner needs to run the course in 138 seconds or 2 minutes. So 2 minutes is what, 120 seconds, right? And 18 seconds. Cool, cool? All right. So that's how you'd use, something that is an arithmetic sequence. All right. Okay, so now let's look at geometric sequences. So a sequence A0, A1, A2 is called a geometric sequence if and only if there is a constant r such that a sub k is equal to r times a sub k minus 1 for all integers k greater than or equal to 1. It follows that a sub n would be a0, okay, and then times r to the n for all integers n greater than or equal to 0. So example 5 has us looking at the population of a country. It's increasing at a steady rate of 3% per year. So if the population is 50 million at a certain time, what will it be 25 years later? Okay, well, how could we look at this? We know that it's increasing at 3% per year, right? But you have to be a little bit careful here because you have that 3% is just the amount of increase, but when you're looking at this, don't we have to figure in, 100, it keeps 100% of the people and then keep from the year before and then keeps increasing it. So the R that we're working with would be 100% plus 3%, right? which would be 1.03. Cool so far? All right, so now we're starting out with 50 million people, right? So we could say P for population. Population 0 is 50, and we'll just remember that it's in millions of people. Okay, so how would we set this up? Well, A sub n would be equal to 50 times the r, which was 1.03 raised to the n. So therefore, A25 is going to be 50 times 1.03 raised to the 25th. So we end up getting approximately 104. If you just put in the 50, you'll get 1047, but that's in millions, right? So when we answer, that's in millions. So when we answer the question, right, we would need to say that 25 years later, the population will be 104.7 million people. Or you could write it like this: 104,700,000 people. Cool, cool? All right. So moving on to second order linear homogeneous recurrence relations with constant coefficients. A second order linear, and sorry, I forgot a blank for you. So linear homogeneous recurrence relation with constant coefficients is a recurrence relation of the form A sub k is equal to capital A times A sub k minus 1 plus capital B times A sub k minus 2 for all integers k greater than or equal to some fixed integer, where capital A and capital B are fixed real numbers with B not equal to 0. Because if B was equal to 0, it would zero out the term. So note that second order relates to the fact that the expression for A sub k contains the two previous terms, A sub k minus 1 and A sub k minus 2. So the fact that we've got this term and this term make it where it's second order, okay? It's linear to the fact that the total degree of each term is the same. Thus, there is no constant term. Okay? And constant coefficients to the fact that A and B, capital A and B, are fixed real numbers that do not depend on K. All right? So, here we go. There's some different cases that we will look at. The distinct roots case is what we'll look at first. So we're going to be working with this expression here, or this recurrence relation. So this is just some general second order linear homogeneous recurrence relation with constant coefficients. So a sub k equals capital A times a sub k minus 1 plus capital B times a sub k minus 2 for any k belonging to the integers such that k is greater than or equal to 2 and where a and b are fixed real numbers. So let's think about this. What if you had a sequence made up of all of zeros, right? So what if a sub I were equal to 0 for all I, right? Well, then you'd just have 0 equals a times 0 plus b times 0, right? And isn't it true that 0 equals 0? So that checks out, right? So that works out. But it turns out that there's other non-zero solutions too. So this is what we're going to be looking at, okay? Let's suppose for some non-zero number t, because we already showed that 0 is a solution, the sequence 1 t squared t cubed t to the n, and then continuing in that manner, satisfies this given relation. So what does this mean? I mean, this means that each term of the sequence is going to be a times the previous term plus b times the term before that. So what would we have? What we would have t raised to the k would be equal to a times t raised to the k minus 1 plus b times t raised to the k minus 2, right? For any k belonging to the integers such that k is greater than or equal to 2, all right? Now, if we let k equal to 2, what are we going to have? We end up with something that is quadratic in form, right? We would have t squared is a times t plus b. Or if we got 0 on one side, hence the term homogeneous, we would have t squared minus at minus b is equal to 0. Good so far? And as we talked about, this is quadratic in form. So the values of t, which make the quadratic equation true, can be found how? Well, factoring, right? Starts with F, it's not a bad word. The quadratic formula, or completing the square, right? Those are skills that you learned before, I promise. So let's check it out, okay? Let's make sure it works, right? So if we take this t squared minus a times t minus b, and it's equal to 0. If we multiply both sides by t to the k minus 2, are we going to get this equation back? Well, let's check it out. We'll have t to the k minus 2 times t squared minus a times t to the k minus 2 times t to the 1 minus b times t to the k minus 2 equals 0. So this product here is just going to give us t to the k, and then we'll have minus a times, good, t to the k minus 1, and then minus b times t to the k minus 2 is equal to 0. And then if we isolate t to the k, we would get a times t to the k minus 1 plus b times t to the k minus 2. So that all checks out, all right? So now let's take a look at this lemma, which will be nice to use. Lemma 5.8.1 says, let a and b be real numbers. A recurrence relation of the form a sub k equal to capital A times a sub k minus 1 plus capital B times a sub k minus 2 for any k belonging to the integers such that k is greater than or equal to 2, to keep it second order, right, is satisfied by the equation 1t squared t cubed all the way to t to the n and on, right? Where t is a non-zero real number if and only if t satisfies the equation t squared minus a times t minus b is equal to 0, all right? So here we go. We'll start with another definition. Given a second order linear homogeneous recurrence relation with constant coefficients, so this is just the same format we've been looking at right here in the same conditions. It turns out that the characteristic equation of the relation has a name, and it is this one, t squared minus a times t minus b is equal to 0. All right? So that officially has a name of the characteristic equation of the relation. So now let's take a look. In example 6, we've been given this recurrence relation, right? And so we want to find all the sequences that'll work out, all right? So here, if we look at b sub k, right, this is equal to 7 times b sub k minus 1, and then minus 10 times b sub k minus 2. I want to match this format, right? So here, notice that there's an addition symbol here, right? So if I wrote this exactly, I would have b sub k is 7 times b sub k minus 1 minus a negative 10, right, times b sub k minus 2. And so therefore, oh God. plus negative 10 times b sub k minus 2. So do you see that our a would just be 7, and then our b would be negative 10. Those are the fixed numbers. And we get that from, here's the a, and then the b is negative 10. So let's see what we've got. When we want to switch it over now to the characteristic equation of the relation, what would we have? We would have t squared minus a times t, right? So minus 7 times t, and then minus negative 10 is equal to 0, which simplifies to t squared minus 7t plus 10 is 0. Now this one, do you see, is factorable, which is nice. So this factors as what? Awesome. T minus 2 times t minus 5 is equal to 0. So we would get t is 2 or 5. These values that we got are not, they represent values for t, right? So basically 1, 2, 2 squared, 2 cubed, dot, 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 2 to the n, dot, 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 and 1, 5, 5 squared, 5 cubed, dot, 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 5 to the n, dot, dot, dot. Those two sequences are going to satisfy our given relation. So they're going to satisfy the sequence b sub k equal to, remember that was what, 7b sub k minus 1 plus 10b sub k minus 2 with its initial conditions, where b0 was equal to 2 and b1 was equal to 2. Cool, cool? Kind of fun problems, I think. All right, so next up, we've got this lemma here. So if we've got two sequences now, R0, R1, R2, dot, 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 and S0, S1, S2, dot, dot, dot. There are sequences that satisfy the same second-order homogeneous recurrence relation with constant coefficients. And C and D, if C and D are fixed numbers, then the sequence A0, A1, A2, etc., defined by the formula A sub n equal to C times R sub n plus D times S sub n for any n belonging to the integers such that n is greater than or equal to 0 also satisfies the same recurrence relation. Okay, so let's check it out. So this proof, well, what do we have to do? What's the evil plan? Really, it turns out to be a bunch of algebra, right? So let's define them, all right? Let's define them, meaning these sequences, right? Because they are sequences that satisfy the same second order homogeneous recurrence relation, right? So first off, we're going to suppose that R0, R1, R2, dot, 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 and S0, S1, S2, and so on are sequences, and that for some A and B that are just numbers along to the reals. We've got R sub k is equal to capital A times R sub k minus 1 plus capital B times R sub k minus 2. So that's just using the definition for this fact that it's a second order linear homogeneous recurrence relation. And we're going to let S sub k equal to A times S sub k minus 1 plus B times S sub k minus 2. Because remember, they satisfy the same second order homogeneous recurrence relation, all right, with constant coefficients. And this is true, for any k belonging to the integer such that k is greater than or equal to 2. So now, why don't we suppose that C and D belong to the reals, okay? And let A0, A1, A2, ... be the sequence defined by, guess what? A sub n is equal to capital C times, what do you think? We want to combine them, right? So R sub n plus capital D times S sub n for any n belonging to the integers such that n is greater than or equal to 0, right? So now, okay, well, we have to take a look at what this would be in terms of k, all right? So let's do it. Capital A times A sub k minus 1 plus capital B times A sub k minus 2 is going to equal to A times, well, what was A sub n? Good. A sub n is defined up here. And instead of n's, what are we using? We're using, good, we're plugging in k minus 1. All right? So we'll have A times C R to the k minus 1 plus D S to the k minus 1 plus B times C R to the k minus 2 plus D S to the k minus 2. Good so far? So now if we multiply, we'll have A times C times R sub k minus 1 plus A times D times S sub k minus 1 plus B times C times R sub k minus 2 plus B times D times S sub k minus 2. Well, if we rearrange them and factor out something different, right, we would have what? Well, if we factored out a C, right, we would have A times R sub k minus 1, right, plus B times R sub k minus 2. So the reason for that is that we get the R's together, all right? And then do you see how we can get the S's together by factoring out a D? So we would get A times S sub k minus 1 plus B times S sub k minus 2. But what are these? I mean, isn't R sub k equal to this? So we would get C times R sub k plus D times, isn't the other one going to equal to S sub k? And that's what we needed to show. Cool, cool? All right, so next up, we're going to look at this lemma called the distinct roots theorem. Suppose a sequence A0, A1, A2 satisfies a recurrence relation. A sub k is equal to capital A times A sub k minus 1 plus capital B times A sub k minus 2 for some real numbers A and B with B not equal to 0 and all integers k greater than or equal to 2. If the characteristic equation, which would be good, t squared minus A times t minus B is equal to 0, has two distinct roots, r and s, then A0, A1, A2 is given by the explicit formula A sub n is equal to C times r to the n plus D times s to the n. Isn't that cool? Where C and D are the numbers determined by A0 and A1. So let's take a look at the single root case, all right? And then we'll go from there, all right? So the single root case, now we're going to go back to that recurrence relation we were working with. And last time we were looking at them as there were distinct roots, right? But now let's suppose it just has a single root, r, okay? So if we do this, we'll have, what is true? I mean, since r is the unique root, of the characteristic equation t squared minus at minus b equals 0, what do we know? We know that t squared minus a times t minus b is equal to, beautiful, t minus r, the quantity squared, because that gives you a repeated root of r, all right? And what is that? Well, that is equal to, well, remember, you've got t squared minus 2 times r times t, and then you'd have plus r squared, wouldn't you, when you expand them out? So let's think about it. What would your a and your b end up being? Because remember, this is all still equal to 0. So let's clean it up. See if we had t squared minus 2 times r times t, and then minus negative r squared is equal to 0. Okay? Because it's the characteristic equation, all right? So what do we know? We know that our a is, beautiful, 2r, and our b is negative r squared. Good so far? And that's just from right in here. That's our b, and our a is the 2r. Okay, so now if we were to let S0, S1, S2, on and on be the sequence defined by the formula S sub n is equal to n times r to the n for any n belonging to the integers such that n is greater than or equal to 0. Well, what could we say? I mean, if we were looking at a times s sub k minus 1 plus b times s sub k minus 2, what would that be equal to? Well, if we plug in k minus 1, what would happen? We'd have a times k minus 1 times r raised to the k minus 1. And then plus b, because with b we have s sub k minus 2. So we would have k minus 2 times r raised to the k minus 2. Because, and again, remember these are, because we have the same root. So just so you see where we're going here, n for n, I'm doing whatever the subscript is, okay? So we have the first one, the subscript was k minus 1, and the second one, the subscript was k minus 2. Okay. Well, what is this going to be? This is going to be equal to what? Well, what was A? Beautiful. A was 2r, right? And so we'll have 2r times k minus 1 times r raised to the k minus 1. And B was? Awesome. Negative r squared. And then times k minus 2 times r raised to the k minus 2. So again, just so you can see what I plugged in here, I know it gets a little confusing. This was our B, and the 2r was what A was. Well, what's this going to be? If I go ahead and combine the r's, meaning that r to the 1 times r to the k minus 1 would be 2 times k minus 1 times r to the k, right? And then we'll have what? Minus k minus 2 times r to the k. Good so far? Because r squared times r to the k minus 2 is r to the k. But what is that? I mean, if you factor out an r to the k, what would we have? We would have 2 times k minus 1 minus quantity k minus 2, which is r to the k times 2k minus 2 minus k plus 2, which is what? Beautiful. K r to the k, because all of this was equal to k. And that, of course, is equal to s sub k. Good so far? So for this lemma here, we'll have a and b be real numbers, and we're going to suppose the characteristic equation t squared minus a times t minus b equal to 0, this should be lowercase, has a single root r. Then the sequence is 1, r to the 1, r squared, r cubed, all the way to r to the n, and 0, r, 2r squared, 3r cubed, all the way down to nr to the n and non. Both satisfy the recurrence relation a sub k equals a times a sub k minus 1 plus b times a sub k minus 2 for all integers k greater than or equal to 2. So this brings us to the single root theorem. So if we have a sequence a0, a1, a2 that satisfies a recurrence relation, a sub k is equal to capital A times a sub k minus 1 plus capital B times a sub k minus 2 for some real numbers a and b, with b non-zero and all integers k greater than or equal to 2. If the characteristic equation t squared minus a times t minus b equal to 0 has a single real root r, then a0, a1, a2, ... is given by the explicit formula a sub n is equal to c times r to the n plus d times nr to the n, where c and d are the real numbers whose values are determined by the values of a0 and any other known value of the sequence, okay? So we'll bring it together in this last example. Okay, so do you see that our a, if we rewrote t sub k, all right, as 6 times t sub k minus 1 plus negative 9 times t sub k minus 2, do you see that our a would be 6 and b would be negative 9? We cool with that? So what would we have? We'd be working with t squared minus, so remember our characteristic equation is t squared minus a times t minus b is 0, all right? So t squared minus 6 times t minus negative 9 is equal to 0. And our a was 6 and our b was negative 9. So now, okay, well, what is this? This is t squared minus 6t plus 9 is 0, but that ends up factoring, remember, as t minus 3, the quantity squared is equal to 0. So that's going to be a single repeated root, right? So, okay, well, from this lemma right here, we're going to utilize this explicit formula. A sub n is c times r to the n plus d times nr to the n. So, working with that, we're working with a sequence t. So t sub n is going to be c r to the times r to the n, I'm doing it in general first, plus d times n times r to the n. Good so far? Okay, so we know what? We know that t has to be equal to 3, right? So t sub n is equal to c times 3 to the n plus d times n times 3 to the n. Cool so far? Now we know t0 and t1, do we not? So what do we get? We get a system of equations. Isn't that groovy? So let's check it out. We need to find the terms that correspond, right? Or we know the terms. So let's plug in what we know. So t sub 0 is going to be equal to 1, right? Well, t sub 0 is also equal to what? C times 3 to the 0 plus d times 0 times 3 to the 0. Good so far? So these two together and simplifying give us that c is equal to 1 because this all zeroes out and this is c times 1, which is c. Good so far? All right, what about t to the 1? We were given that, or t sub 1. All right, what about t sub 1? We were given that t sub 1 is equal to 3. Well, t sub 1 is also equal to c times 3 to the 1 plus d times 1 times 3 to the 1. And again, I am finding these values, not by magic, but I'm plugging here wherever there was an n, I put in the subscript. So here, that's where we got that one, and that's where we get the second one. Cool, cool. All right, so coming back, combining these, right here we'll just have 3c. Right here we'll have 3d, right? So that gives us 3 times c plus 3 times d is equal to 3, or c plus d is 1. Now bringing both of these together, what do we know? Well, c is 1, right? So 1 plus d is 1 means that d must be 0. Putting it all together, we're going to have, so remember this was our t sub n, so we're going to have t sub n is equal to, we know that c is 1, right? So 1 times 3 to the n plus d is 0, so we'll have 0 times n times 3 to the n. So our t to the n is equal just to 3 to the n for all n belonging to the integers such that n is greater than or equal to 0. Cool, cool? All right, so we're done. And that wraps up the lesson for today. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. If you like what I'm doing, please subscribe and tell all your friends. Bye.